Alright, it's been a while since we last met. So I'm just going to sort of pick a point where we can start lecturing and take off from there. I think the last thing that we were talking about was gas particles and how gas particles are far away from each other and they travel in straight paths until they collide with each other, then they'll change direction, keep changing direction, and that's basically how they behave. And they're so far away from each other that there's no attraction or repulsion between them. That is not the case for liquids. Let's take a look at liquids. So let's say we wanted to focus on water molecules that are found in a lake. Unlike gases, liquid molecules are very, very close to each other. As you see here, they're very close to each other. And this is because they exhibit what are called intermolecular forces. So they have very strong attractions with each other. They can slide past each other, move across each other, but it's very hard for them to escape because they're very attracted to each other. They can spin around, they can rotate, they can slide past each other, all that business. They're just constantly doing that. So that's happening in a lake. They're just constantly moving around. So they do have a lot of kinetic energy, but not as much as gases. In order for them to leave the liquid state and enter a gaseous state, they have to have way more kinetic energy that overcomes the intermolecular forces between them. So, because they have intermolecular forces, they are much more dense than gases, and liquids and solids are considered condensed states of matter. So let's consider a sunny day by the lake. What's happening is that sun, right, is providing a lot of energy. And as this energy is passing through the atmosphere, it's giving a lot of particles extra energy. It's giving the air molecules energy so they can travel faster. So you can expect an increase, right, in their movement and pressures. And this is just from the particles in the air, but you also have interaction with the surface of liquids. Well, you probably know what happens over time to any body of water. It evaporates. So what's actually happening during evaporation? Liquid molecules, in this case the water, gain enough kinetic energy to escape the intermolecular forces and they can enter a gaseous or vapor state. Now, when a liquid turns into a gas, that is called vaporization. However, when it's not happening at boiling point, for example, what's happening over the lake, that is called evaporation. So evaporation is the same thing as vaporization. It's going from a liquid to a gas state. However, it's called evaporation because it's happening at a temperature that is less than the boiling point. Again, when a water molecule gains enough kinetic energy to escape the intermolecular forces, it can leave the other water molecules. Now, sometimes they can collide with another molecule and bounce right back in, or sometimes they're able to escape and enter the atmosphere. Now, evaporation is considered a cooling process. I know it seems kind of weird, but it'll make sense. Think of it like this. The hotter molecules are traveling faster. Well, if the hotter molecules are the ones leaving, then you're leaving behind a cooler system. This should make sense to you because anytime you've ever gotten really hot and you kind of started sweating, well, the reason you sweat is so that the water can evaporate from your face. And it takes a lot of the heat or the particles, right, that have greater kinetic energy with it, And since those hotter molecules are leaving, you're left with a cooler sensation. So anytime you ever had a lot of sweat on you and then a breeze passes by and some of those sweat molecules evaporate, you feel that cool on you. All right, so let's consider this scenario. Let's say we have a beaker, and in this beaker we have water. Now, what's going to happen is, over time, as these water molecules are moving around, some of them just might gain enough energy to leave the system. Right? So you may have some enter a gaseous state. Right? So they're sort of leaving, right, the liquid phase turning into gas phase. That's very possible. It's also possible that some of the water molecules in gas phase will come back and come into contact with the liquid. And when it does, the intermolecular forces are so strong, it keeps it there. But over time, if we wait, more and more water molecules will enter the atmosphere, and you can expect a decrease in the volume of the water because they're evaporating away. Right? That's why we know that if we wait a very long time, any body of water is going to decrease over time. Because we have gas particles being formed, right? These gas particles that are rising out of the water. Well, if we're creating gas molecules, these molecules are colliding with the walls, they're colliding with each other, they are creating a pressure. This pressure is called vapor pressure. So we now need to consider two scenarios. In one scenario, we have an open container, and this open container has a certain volume of water. And let's say we have another container, but this container is closed, and it has the same amount of water in the container. Well, if we were to let the clock go, that's horrible. If we were to let time pass, what would we expect to happen? Well, hopefully it should be obvious that in both cases we're going to start to have evaporation or vaporization. We expect the water molecules to sort of gain some kinetic energies and possibly escape, exit the water. And that'll happen in both cases. The problem is that in the open container, the water molecules are going to keep bumping into each other or bumping back into the water, but eventually, for the most part, they're just going to keep escaping the container. So they're going to leave all this. Whereas in the closed container, they cannot leave. So what's going to happen is they're going to keep filling up this empty space until it gets to a point where the water molecules are leaving the liquid state at the same rate at which water molecules are coming back into contact with the liquid state. So these rates would be equal to each other. When your rate of evaporation equals your rate of condensation, you have what is called equilibrium. The rates are the same. In the open container, you're never going to reach equilibrium because the rate of evaporation is going to be higher than the rate of condensation. Water will be leaving the open container at a much greater rate than the water molecules coming back down and colliding with the water. Okay, and I just want to wrap up again, just real quick, kind of discussing the differences between evaporation and boiling. It's not just water molecules that can come back down and collide with the water in the liquid. it can also be the air molecules. You have atmospheric pressure above any body of liquid. So just like water molecules that are leaving can collide with particles and collide back down into the liquid, air molecules are also pushing down on a surface of anything, on the surface of a solid or surface of a liquid. So whether something's evaporating or boiling, they still have air pressure coming from the molecules that are of air in the atmosphere above a liquid. So we have two kinds of pressures. You have atmospheric pressure pushing down, and you have vapor pressure pushing up in both of these cases. So the way that it's defined is when your atmospheric pressure is much greater than your vapor pressure, then it's not boiling yet. So you are not going to see any kind of bubbles in a system. No bubbles. So anyone who's ever made pasta, you know that as you're heating it, some of the water molecules, they're getting hotter. There is a little bit of evaporation taking place, but you're not going to see any bubbles. It's not until you see bubbles, it's not until you see bubbles that you know it is evaporating, and that it is boiling. And when you see bubbles, what that means is your atmospheric pressure and your vapor pressure are equal to each other. That is the definition of boiling. So, again, in evaporation, the atmospheric pressure is much larger than the vapor pressure. In boiling, they're at least equal to each other. Which is why boiling water at sea level versus boiling water up on a mountaintop is not going to have the same boiling point temperature or boiling temperature. Down at sea level, the boiling point of water is 100 degrees Celsius. That means that at sea level, where the atmosphere is equal to 1 atmosphere, at 100 degrees Celsius, your atmospheric pressure is equal to the vapor pressure rising out of the liquid. However, at a much higher altitude, where the pressure is lower, so it'll be less than 1 atmosphere, then there's going to be less air particles pushing down on the surface, so you don't need as much water vapor leaving the liquid water. So it takes less energy, right, less kinetic energy for these particles to escape. So you may see something like the 94 or 96 degrees Celsius is the boiling point of water with a higher altitude. So that's kind of the relationship between vapor pressure and temperature. Right before we left on our forced spring break vacation, we had seen a graph that looked something like this. We had different substances that had different curves on them, something like this. And the general idea is this: with an increase in temperature for all of them, as temperature is going up, their vapor pressure is rising. The only difference is that in some cases, it takes less temperature. Now, if we were to consider water, for example, water would be this one right here. If we looked at 1 atmosphere, or that's the same thing as 101.325 kilopascals. So at that temperature, we would just follow the line, hit the water curve, look straight down, and lo and behold, we would see something like 100 degrees Celsius. Well, we can use this graph if we wanted to say, okay, well, what if we were at 0.9 atmospheres? Well, you just follow the curve till you hit the water, and then drop back down, and then notice, well, it's not that big of a difference, say 96 degrees Celsius or something like that. So you can use these curves to predict the boiling points of a substance. All you have to do is look when that vapor pressure that you're looking at hits the curve that you want. For example, this first curve is chloroform. So if you wanted to know what its boiling point would be at, say, 0.5 atmosphere, you would just move along till you hit that curve, move downward, and whatever temperature value you have, that is the boiling point of chloroform at that pressure, which is not the same at sea level pressure, right? Those are two different pressures, and they result in two different temperatures.